All right, so here we are with an example. It says, according to an article in the San Gabriel Valley Tribune, most people are kissing the right way. That is, according to a study, the majority of couples prefer to tilt their heads to the right when kissing. In the study, a researcher observed a random sample of 124 kissing couples and found that 68 out of 124 tilted to the right. So this is how it's going to be worded. Is this convincing evidence that couples really do prefer to kiss the right way? Okay, so what we have here from our random sample is we have my sample proportion, 68 out of 124, which is 0.548. Okay, so we're going to go through the four-step process here, and we're going to start with the state. Now, with the significance test, the state is a crucial part. And again, remember, you don't have to put like state, plan, do, conclude, but you have to address all four elements. So this is a significance test. For an interval, we said we want to estimate. For a test, we say we want to test. So we want to test the following hypotheses. And we also want to set up our level of significance right away. It doesn't ask us to do a particular level of significance, and so we'll just make one up. Typical alpha values are 0.01, 0.05, or 0.10. So I would say like a typical value to choose if you're not sure which one to go with would be a 0.05, and that's just fine. Okay, so then the null hypothesis and the alternative hypothesis. This is a question about proportions, and so we want the true proportion. It says most people are kissing the right way. Okay, so is this evidence that they really do prefer to kiss the right way? So the null hypothesis would be that there is no difference, that there is no preference for which side, and so it would be like a 50-50 chance that you would kiss to the right. And it says, do we have evidence that they prefer to kiss the right way? So a preference for kissing the right way would mean greater than here, that there would be more people who would kiss the quote-unquote right way. We also want to make sure to define what P is, where P is the true proportion of couples who quote-unquote kiss right. Okay, so what are the elements that are required here? You need to have a level of significance somewhere on your page. That doesn't have to be in the state criteria, but generally when they give you grade scores for a significance test, there's four things that they're looking at. So the first thing is all the setup. So you've got an alpha value, you have your hypotheses, and you've defined your parameter of interest. So those are really the three things that are the first score criteria on the AP exam. Now the plan is where we talk about conditions. If the conditions are met, we will do a one sample. So before it was a one sample Z interval for proportions, or a one prop Z int. This is a one sample Z test for proportions, or a one prop Z test. Check our conditions random. We are told we have a random sample. A random sample of couples. I'm thinking that we're probably sampling without replacement, and so I'm going to check the 10% condition. We are sampling most probably, sampling without replacement. However, let's think about this. We have 124 in our sample. Is it reasonable that there might be more than 1,240 couples in the population, whatever that population may be? I think that they're talking about all couples in some larger population. So I think that seems reasonable. It seems reasonable that there are at least 1240 couples in the population. So this condition is met. So then for proportions, is it large samples or large counts? I hope you said large counts. This is the NP and N times 1 minus P. But remember that we have to keep in mind whether or not this is P, P naught, or P hat. We, in a test, are always checking with the hypothesis, and so this is the P naught value. So we have 124 times 0.5, and over here we'd have 124 times 0.52, which is equal to 62, and so both of these values are greater than 10, and so this condition is met. And this condition has to do with determining the shape of the sampling distribution of the sample proportions. So this allows us to approximate normality of the sampling distribution of the sample proportions. Now we do. So the do in formula would be P hat minus P naught over P naught, 1 minus P naught all over N. For this problem, we have 0.548 minus 0.5 all over root 0.5 times 0.5 over 124. We get 1.078. And you can use your chart or you can go to your calculator. So let's see, this is a z-score of 1.08. And I'm looking for, okay, so here's the thing. Let me draw my picture. Okay, here's the hypothesized value, and I have a z-score here of 1.078. I'm interested in this p-value that's up here. So area to the right. Okay, so let's see. Going to the chart, I get a p-value of 0.1401. And you could use your calculator as well. So p-value equals 0.1401. Okay, so the required elements in the do step. You have to have the name of the test either by name, which you've done up here already, a 1-prop z test, or by formula. Okay, so you have to have one or the other, either by name or by formula. You should show the values plugged in. You should show the z-score. You should show the p-value that you get. Drawing the picture is helpful as well, but not required. But I encourage you to certainly do sketch the distribution, because this is going to remind you about the connection regarding evidence or not. Okay, so when you conclude, so the conclusion is based on where the alpha value is. Okay, so the alpha value that we had was 0.05. That means the area under the curve is equal to 0.05. So I need to put a vertical line here in my picture such that the area to the right is 0.05. So 0.05 is smaller than 0.14. So my alpha value would be here, such that the area to the right is 0.05. So now my decision about rejection or not rejection is based on where the p-value is. Okay, now since the cutoff for the p-value is not beyond the alpha value, then I fail to reject. So anything over on this side would be rejection, and anything this side would be fail to reject. And that means failing to reject the null. Meaning that my sample value isn't far enough away for me to not believe that the null hypothesis is a plausible value. So here's how I write this. Since the p-value of 0.1401 is greater than an alpha value at 0.05, then we fail to reject. We fail to reject, and you have to say what you're failing to reject. We fail to reject the null hypothesis. Okay, if I fail to reject, that means that we do not have convincing evidence. Remember, we're always trying to have evidence for the alternative. My alternative isn't far enough away to meet the cutoff point. And so I don't have enough evidence here, and then put it in context, that couples prefer to tilt their heads the, quote, right way when kissing. So, here we have a full test. 4-step process. Nothing super duper amazing going on. I mean, it is pretty amazing, but like, you should feel comfortable at this point with the 4-step process, understanding conditions are for the plan, do is where you calculate, conclude is where you conclude. And the only thing that's new really is this idea about the rejection or the fail to reject region. Okay, so here's a question. What happens if the data doesn't support the alternative? So if we look at our alternative hypothesis, right? Our alternative hypothesis was that we were interested in evidence that couples really do prefer to kiss the right way. Let's suppose for a minute that the alternative was p less than 0.5 with a p-hat value of 0.548. If I drew that picture, let me scroll up here. So if I drew that picture, here's the null hypothesis at 0.5, and I have a z-score here at 1.078. But then because it's going to the left, because my alternative hypothesis is looking to the left, I'd be shading on the left-hand side. This has a p-value of 0.859, which is huge. So if your data doesn't support the alternative, then why would I continue with the test? Clearly, my data is in support of the null hypothesis. And so why would I even continue with the test if my sample value didn't coincide with the alternative? I would encourage you to read on page 560. On page 560, it talks about this idea, like what happens when the data doesn't support the alternative. Again, it's on page 560. I'll write that down for you. Okay, so read page 560. And I'll just write it out here too. Such a sample doesn't give any evidence for the alternative. Remember, that's what we want. We want our evidence in support of our alternative. So why would we continue with the test? Clearly, we're going to fail to reject. Clearly, we're on the side of the null hypothesis, so we would fail to reject. Okay, so let's take a look at another example. This one's just a slightly different one, but we're going to go through the same 4-step process again. It says, when an accounting firm, AJL and Associates, audits a company's financial records for fraud, they use a test based on what's called Benford's Law. Benford's Law states that the distribution of first digits in many real-life sources of data isn't uniform. So, like, the probability of selecting any number from 0 to 9 in a just, like, random number selection would be the same, 0.10. But in financial records, that's not the case. So in financial records, it says there is no fraud. About 30% of the numbers in financial records begin with the digit 1. However, if the proportion of first digits that are 1 is significantly different from 0.301, then they do a much more thorough investigation. So suppose a random sample of 300 expenses from a company's financial records results in only 68 expenses that begin with the digit 1. Should AJL and Associates do a more thorough investigation of this company? Okay, so we want to test the null hypothesis of P equal to 0.301. So when there is no fraud, the claim is 30.1%. Versus the alternative, it says if we're significantly different from 0.301. It doesn't give us a direction, so not equal to 0.301, where P is the true proportion of expenses that begin with the digit 1 for this company. And we should choose an alpha value, 0.01, 0.05. I chose 0.05. Okay, so the plan, we're going to do a 1 prop z-test if our conditions are met. Random. Do we have a random sample? Oh, great. In a random sample, so we are told we have a random sample of records from this company. Let's see, if we have a sample of 300 times 10 would be 3,000. Would it be reasonable to think that there might be 3,000 financial records for a large company? And I think that would be true. So it is reasonable to assume there are more than 3,000 expense records in this company. Large counts condition, and P naught, let's see, that meant to be an equal sign there. So N is 300 times 0.301, gives us 90.3, which is greater than or equal to 10. N times 1 minus P naught, so we have 300 times 0.699, which is 209.7, which is greater than or equal to 10. And so this condition is met. And so we're ready to go on. I like to put the formula P hat minus P naught root P naught 1 minus P naught all over N. It just reminds me, just gets that muscle memory going. Sample proportion, let's see, 68 expenses out of 300. The hypothesized value 0.301, and then 0.301, 0.699 over 300. So it'd be super awesome, and I bet our calculator can do this work for us. So if we go to Stat Tests, this is a 1 prop z test, number 5. So P naught is our hypothesized value, and we have oh my gosh, 0.301, x is 68, n is 300, and here's where you choose your alternative hypothesis. So our alternative hypothesis is not equal to, and then you can either calculate it or draw it. I'm going to calculate it here. So this gives me the z-score, negative 2.807. It also gives me the p-value. The p-value is 0.005. So this is nice because then I don't have to go to the table. But I do want to point out to you that if I go to the table, let's see, if I go to the table, let me draw the picture first of all. Here's our null hypothesis at 0.301, and we have a z-score of negative 2.807, but it's a not equals to, so there's really another one over here, 2.807. If I go to the table and I find negative, I'll just call it negative 2.81. If I go to negative 2.81, I get 0.0025. 0.0025. That's this region. And this is also 0.0025. When I add them together, I get 0.005. So you have to add them together. So if you're going to do it from the table, you have to understand that in the table, you get only one side. You have to multiply it by 2 to get the total p-value for this problem. Okay, so then how about rejection? Okay, well, so the p-value, oops, conclude. So our p-value, 0.005, is less than 0.05. Since our oops, sorry, that's not really your bell. Since the p-value of 0.005 is less than alpha, which was equal to 0.05, then we reject the null hypothesis. And I like to always do this in favor of the alternative, just to remind me what's going on. If we're in favor of the alternative, then that means we have convincing evidence that the true proportion of expenses that begin with 1 for this company is different than 0.301. The question is, should AJL and Associates do a more thorough investigation of this company? So yeah, if the proportion of digits are significantly different, then that could mean that there is fraud. So you want to make sure to answer any additional questions that are there in the problem. Therefore, AJL and Associates should investigate further. That's a further with an H. Okay, so I want to mention 2 things. So one last thing about this problem is with regard to the picture and the significance level. So we have a significance level of alpha equal to 0.05. When I have a two-tailed test, that means that the alpha value has been divided in 2. So the alpha value is 0.025. And okay, now I'm not really speaking properly. The alpha value is 0.05, but the cutoff, I'll put cutoff here, is 0.025 on either direction. So if these vertical lines were inside this region, then I would be failing to reject. But since the cutoff is here and the area is beyond that, away from the null hypothesis, if I'm away from the null hypothesis, then I reject the null hypothesis. So the alpha value in its entirety is 0.05. But if I were to put it on the picture, I would say that it's 0.025 are the cutoffs on either side. The other thing I wanted to point out is just we didn't do the test on the calculator for the previous problem. So just really quickly, if we go back to the kissing problem, we have a stat test. It's a 1-prop Z test. This one was 0.5 in the null hypothesis. We had 68 out of 124, and our alternative hypothesis was greater than. You can calculate that. We got a z-score of 1.078 and a p-value of 0.1406 on the calculator. I would make sure to be consistent there if I'm going to use my calculator. And then everything else we have talked about there. You can draw it. So if you go back here and you do the draw instead, so it draws a normal distribution, and it's just like the picture that we drew. The only thing is that it doesn't show me the cutoff for rejection, but it does in fact draw the same picture that we have, that normal distribution. Okay, so can you describe a type 1 and a type 2 error in the context of the Benford's law problem? Let's see. Type 1 would be to reject a true null. So rejecting a true null, rejecting a true null. Okay, so the true null is that it's equal, but we reject it in favor of the alternative. So this means that we think the true proportion of digits is not 0.301 when really it is. And so what we would say a consequence is that we would perform a more thorough investigation unnecessarily. We think that there's a difference in the first digits when really there isn't. A type 2 error is just the opposite of that. We're going to fail to reject a false null. We think that p is equal to 0.301 when really it's not. So we have the fraud investigation not performed. And the company could be fraudulent. Sometimes you're asked to decide which one is more serious. In the case of the drinking water, I think the death was most serious. Here, I would think that the type 2 error would be most serious. Fraud was, the company could be acting fraudulently and it wasn't caught, as opposed to performing a thorough investigation unnecessarily. While that would cost more money, I think that the type 2 error in this case would be the more severe. So sometimes you are asked to make a decision about whether or not you think it's, like which one you think is more severe. Now there is a confidence interval relationship between significance tests. And so the question here says, can you use confidence intervals to decide between two hypotheses? And the answer is yes. What is the advantage to using a confidence interval for this purpose? And why don't we always use confidence intervals? Okay, well, so remember when we described confidence intervals in the last chapter? If I have a 95% confidence interval, then that means that I have 0.025 and 0.025 in the tails. So a two-tailed test at an alpha level of 0.05, right? We just saw this. We just saw this cutoff of 0.025 with an alpha level of 0.05 with a two-tailed test. If you have a two-tailed test at an alpha value of 0.05, this is consistent with a 95% confidence interval. So why don't we always use confidence intervals? Well, we may not have enough information. Maybe we just really want to do a test. I mean, a confidence interval actually kind of gives us a little bit more information about the two-sided test because it gives us a good estimate for what the real value is, and we can compare that with the hypothesized value. So here's one last little question, and then we'll be done. I know it's been a long lecture today. So we have a 95% confidence interval for the true proportion of expenses beginning with the digit 1 for this company to be 180 to 0.274. Does the interval provide convincing evidence that the company should be investigated for fraud? So here's the interval. And so again, when you're making decisions about a confidence interval, it's about what is or is not in the interval. The value of interest was 0.301. Remember, the null hypothesis was p equals to 0.301. And so we would say, because the interval doesn't contain 0.301, okay, that means that this value is not in the interval that I obtain. So that means that I would reject the null here and conclude that the proportion is not 0.301. We reject the null hypothesis and conclude the proportion of first digits of 1 in this company's records is not 0.301. So does that mean they should be investigated for fraud? Yeah, we still have the same conclusion. So same conclusion that we make. Conclusion. So same conclusion that we had from before. How do you know when to reject or fail? You reject the null hypothesis when the hypothesized value is outside of the interval. And you only use a confidence interval to check a two-sided test. Right? A one-sided test is not an interval. It's not like a symmetric about it's not a symmetric distribution or a symmetric thing about the distribution. Okay, so that's it for our notes for today. Big long lecture. You have some time to get started on your homework. And the homework for tonight is here. So since I didn't collect homework for this homework, because the sub is here, you have homework 9.1 and 9.2 going to be on Tuesday. Okay, so you have some time to get started.